All right, so hello everyone on the lecture number 13, last of this semester. But we will, it's not the last of the lecture because we'll continue on after a summer break. So the YouTube viewers won't even notice, I guess, at least the future viewers. But we will have some time to regenerate, I guess. I mean, those of us who will regenerate. Okay, so last time what we did, we basically solved or found a couple of terms. I mean, the lowest order terms for the Schrieffer-Wolff transformation. Can I find them somewhere? I think I can. Oh yeah, we got the energy, lowest order energy correction, and we got the generator of the transformation, the first order. And they are, they are what they are. And then we talked about some applications of Schrieffer-Wolff transformation, which I decided to split into a couple of modes. So there was a diagonalization mode where you basically treat it as you think of it as just a transformation that diagonalizes everything into the eigenbasis of the perturbed Hamiltonian, but in perturbative terms, right? So it's like an approximation. There was an effective theory mode where you basically use this transformation to construct a new effective theory. So you take a big theory and you make it smaller for smaller dimensional system. And there was this third, I didn't even write it, I guess. The third mode, oh, it's here. Oh, can I move pages? Theory renormalization mode, whatever.
And click and then.
Oh, I probably can
move up.
Move up, yes. Move up.
So I think you can click and drag if it's.
It didn't let me.
Yeah, okay. Maybe shift click, control click.
We moved it. Okay. Theory renormalization. It was the idea that, okay, if we can create effective theories, then maybe we can work backwards, right? We have some system with some Hamiltonian, have some terms, but maybe we can come up with justification for this particular model, but this model, it actually came from it's an effective theory of something bigger, right? And it's like, then if you allow for this kind of option, then it's like every, possibilities start to proliferate because, maybe every theory, every Hamiltonian is an effective Hamiltonian of something bigger, right? Sometimes the Schrieffer-Wolff is like the formal transformation that leads you to there, but maybe there are different stuff. And maybe you can even make it more broader because it's like theory in the narrow sense that it's a quantum mechanics with this Hamiltonian, right? This is theory number one. You change Hamiltonian theory number two. This is how I use this narrow sense theory, but also in broader sense, let's say maybe classical mechanics is also an effective theory, right? And it's like probably not Schrieffer-Wolff is not the mechanism through which you obtain it from, let's say, quantum mechanics, but this idea that theories are related to each other, there are no hard borders between them, one flows into another, and there is obtaining an effective theory is inherently like a reduction kind of process. So you get the smaller theory there are effects from this bigger theory, but not all the details are important. So many different big theories can lead to the same small theory, which opens this whole idea of emergence, right? It's so effective laws. I mean, the laws that come from the theory describing, effective theory describing this kind of system, right? They are kind of not, they do not follow straight from the laws of a bigger theory, right? So it's like, it's kind of like, opens up a new way of thinking about the whole physics, you know, the borders between theories and how fluid they are. And Schrieffer-Wolff is maybe the simplest, I don't know if it's the simplest, but the one that we know, like a formal mechanism through which you do this reduction. Or you can also mix and match those modes, or even mix and match with some completely different kind of approximations, like Navid. Like Navid pointed out that the way he's using, because we had in the audience 2 guys who actually use Schrieffer-Wolff in practice. Navid pointed out that, we are doing the Schrieffer-Wolff transformation, but we are using it in this mode of diagonalization, actually, because they like do the transformation to every operator in the problem. But on top of that, they are they are exploiting the fact that they have energy gap. So they are like, on top of that, throwing out the terms that come from, those fast oscillations due to big energy gap. So you can, like, it's a tool. You can use it in many ways, many different ways. So that's a recap. I'm just checking my paranoia that it is recording indeed. So what else? What else is to be said here? So the thing that the way we obtained our terms of this perturbation theory previously was like very, we just came in without a plan and just, let's do some stuff and see what happens. So I guess to close this whole discussion would be like, okay, to actually reevaluate everything and make it like a proper, good and proper. Do the procedural stuff, do the diagrams, check for convergence if we can, and stuff like that. So this last lecture, I want to focus on doing this like a proper way, so that we can see all the formal mechanisms behind this whole idea of Schrieffer-Wolff transformation, and all this stuff is basically I will base this on this source. Okay, this very nice paper with way more detail than we will be using. It's really cool. It's kind of long and but everything that I will talk about is basically comes from this. Some stuff I will skip. So if you want to know more details, you need to know more details, you can find them in this particular paper. Okay. So this is our source material. Yeah.
So here we are approximating the Hamiltonian. So I would expect we approximate the evolution operator because that's the solution, right? So here you are in a way approximating the differential equation before solving it.
Well, we're not exactly approximating the Hamiltonian. We are approximating a transformation that diagonalizes Hamiltonian. So it's like that's why that's why you have to have in mind, always have in mind, what you are doing with your quantum mechanics, right? Ultimately, you want to let me get it. Ultimately, what you are thinking about doing is some correlation functions, right? This is what you would need to calculate. To which I want to find a formula. Beasts like this, right? Which quantities that involve evolution operators, Hamiltonians, if you want eigenbases made out of eigenstates of Hamiltonian, eigenvalues, and so on and so forth. So this is like, we want to have a approximation of a transformation that gives us eigenstates and eigenvalues of the perturbed Hamiltonian, so that we can use it to calculate correlation functions of various kinds. Okay? And this is, if you have this in mind, that's already a lot, because people get confused about this, what Schrieffer-Wolff actually does. Because is it this or that? But if you have this at the forefront of your mind that correlation functions is the thing, then it's like, okay, that it makes more sense what we are doing. So let's try to make it good and proper. So so thing number one is like, so the diagonalization is executed via change of basis with a unitary operator. Unitary operators are basically rotations, if you think about it a bit, because they are isometries, that is, they preserve the length of vectors, and also they preserve angles between vectors. So it's like a rotation, because this is what rotations do. So you can think about, so let me do some sketches. Oh, can I do a better job at plotting a sphere? Maybe not. So if you think about representing vectors, let's say unit length vectors in our head.
A circle shape tool or something like that.
Yeah, I mean I can.
Maybe you can just complete the circle and hold it for a second. Maybe it will automate to a circle.
I don't know if this is such a, if this program does stuff like this.
Wow,
Yeah, perfect. Yeah. I'm so talented. Yeah, sure. Now how to get out of the mode.
Pencil maybe. Yeah.
I just click again. So this is a sphere, not a circle. Okay, sphere. So I should make it 3D. I don't know, 3D, or whatever. And you can visualize that unit length vectors, cats, would be some points on this sphere, right? So let's say this could be like some psi, and let's say this would be some phi, whatever, unit length vectors. And might be elements of basis, one basis, the other basis. And now unitary transformation would execute some, go from one to the other. But there are, you can see, there are a lot of ways to do it, right? For example, you could imagine that you will go first let's go here, and then let's go here, right? So it's so it would be like a rotation around one axis, and then composed rotation about other axis. Or you could imagine that you are doing a rotation about something like this, right? Or you could even go something like, okay, let me go like this, go behind, and finally come here. That's fine. Or you could even do billion revolutions like that.
So it's like moving in a car between 2 points on Earth.
Yeah.
It's but not flight, because you should stay on the Earth. Yeah,
you imagine unitary transformations you're staying on the sphere, but the path you take, you can whatever. If the end point is something fixed, you can go there through infinitely many paths. And you can see most of those paths are inefficient, right? You are wasting a lot of space. The paths are long, but of course you can see that there is this, I can even change the color here, that there is a rotation that you can see that is direct, right? It's the most direct from one point to the other. You just go straight through not straight, but the arc, how do you call it?
Circle, great circle. That's part of great circle.
Yeah, how do you call this thing?
Arc.
Arc. Yeah. It's an arc. Okay. Go arc. That's the closest arc, right? So we would call it direct rotation, let's say, because it's like the most efficient way to do the transformation. And why we should, what kind of things we could expect from this kind of direct rotation, where unitary operators, you have some unitary operator that, let's say, takes psi to phi. They can always be expressed as some, there is a generator there, right? Exponent of some generator. This is some Lie algebra, Lie group stuff. So it can be always generated. And this S, the magnitude of this S, you can imagine that this is like an angle you are, or the length of the path you are going through to reach the final point. So it's like if you go something insane, like do 50 revolutions before you reach your point, the magnitude of this generator would be like 2 pi times something. It would be very big. If you go for a direct rotation, this generation is probably the smallest you can get. And now, so if you want to get a perturbation theory for your transformation, or for the generator of this transformation, you probably want to focus on the direct rotation, because then it might make it small, right? So it's like a couple of terms from your perturbation series would probably reflect, would be easier to obtain, you know, than for some crazy transformation that goes around everywhere. So direct rotation then. So how one makes direct rotation? How one constructs direct rotation? So there is a procedure. So if you are given two vectors, we are given two unit length vectors. So psi and phi, let's stay with psi and phi. And this is an important caveat that are not orthogonal. That is, we want scalar product between bracket between psi and phi to not be zero specifically. Okay, we want them to be not zero.
Why? Or it will become clear later.
Actually, it won't become clear. Actually, it won't become clear. But it's kind of. I don't really have a good answer why. What exactly breaks when it's. I think there is some issue with ambiguity. I mean, maybe we can figure it out.
Yeah, maybe because it's not clear. Because when you think about simple rotations, you can rotate x to y, right? So
yeah, it seems like
that's not probably something else. Yeah, let's see.
I mean, one thing I was like, we'll see.
Yeah.
Maybe we can figure this out. I tried to find a good argument. I mean, the formulas, you can see why formulas break, but...
Preliminary argument could be like, if you imagine the block sphere, the orthogonal states are always antipodal to each other. So there is like, it's an obvious choice, like how you need to rotate to get there the fastest rate.
But it's like...
it's not...
I was always
breaking anything in here.
I would kind of expect that this construction of direct rotation would just simply maybe it would survive still, just give you this that maybe there will be some. I just don't know. Maybe it's just there are infinitely many ways that are equally efficient.
Yeah, but in the case that you said, there is one speciality there that you have multiple options. Because it's not unique, it's you have
that's what I'm saying. That if they are not orthogonal, then there is one unique. But if they are orthogonal, there is infinitely many.
Yeah, because you can connect it with any great circle that is.
Maybe this is the answer. I kinda don't exactly. I was trying to figure this out for a couple of weeks. Like, what is the great argument? But I don't know, but this is very key. Those one-dimensional subspaces are not orthogonal. This is kind of key. So the construction is like, I don't know, maybe for some people it's intuitive, but the way you can create this direct rotation is by using reflection operators. So first you define two operators that change the sign of vector psi and the other that changes the sign of vector phi, but does nothing, leaves everything else alone. And those reflection operators, they are quite easy to construct. It's 1 minus twice the projection on each of those operators. So that would be a reflection of psi. And 1 minus twice phi, that would be a reflection of phi. Now, to see that it is indeed a reflection, so if you take just, r psi on psi, what will happen? So you will get psi because of identity, and you will get minus twice psi on psi. And we assume the length of 1, so this is 1, so just minus psi. Okay? Nice. Now if you take some vector from the complement of psi, anything that's orthogonal to it, you can easily see that this will just zero out, right, and just identity. This is the reflection, just reflects everything parallel to psi and leave everything as without any modifications. And
but when r psi acts on phi, it's a different operation, because we are assuming they are not orthogonal, right? So
yeah,
r psi acting on phi.
Yeah, if I try to do reflection on phi, there will be something
else, yeah.
something non-trivial, right? Because they are not. There is a component that's parallel.
Yeah,
To actually ease these calculations, let us pick a subspace of our Hilbert space that's spanned by our two vectors, because we are interested in doing a direct rotation between them. Okay, so let's isolate the subspace span on psi and phi. Which you can do span even if they are not orthogonal. This would be some plane, effectively, but And this is a subspace of our whole Hilbert space. So in this two-dimensional subspace, we can pick a basis. We can even make it orthonormal. So for example, we can pick a basis that's made out of, let's call it first basis vector, which we can set it simply to be equal to psi. And there will be the other guy. And let's make it orthogonal to 1, to 0, sorry. Okay? We can always do this because Gram-Schmidt orthonormalization, we know we can always do it. And moreover, we can pick this basis in such a way that the psi is just equal to 0 vector, but phi would be equal to cosine theta 0 plus or minus, I mean up to sine something like this, with theta that's smaller than pi over 2. So they are not orthogonal. Okay? We can always choose our basis in this span in this way. So now, once we have this parametrization, the reflection operators, we can actually calculate them explicitly. Yeah?
So you are assuming that there is no complex, the overlap is real.
I can choose a basis. Can I choose a basis?
Because the relative phase will always remain, right?
This is something I can always do.
You can remove relative phase always. That seems to be top.
Yeah.
Because it means like your qubit and so on will.
Yeah. There is some. Now it just escaped my brain, but there is some argument. There is a proper argument you can make that by choosing the basis, you can always set it up in such a. So the scalar product is non-zero. That's what we assume. And now by choosing a basis, not basis. This basis in this span, we can set it up so that the coefficients are real.
And if the inner product has a complex part, we can always observe it in like one, what we define as the basis vector, one. Right?
Yeah, probably something.
Or even psi better,
Yeah.
because we are starting from psi. So that would be.
I was figuring this out like a couple of weeks ago, and now I just forgot what's the proper argument. But it's something you can do. And the guys in this paper, they say it's possible. So, it's not. I'm not hallucinating this. At least I am. Not only I am hallucinating this. No, but this is something you can. Yeah. Whatever the case, with this parametrization, we can actually calculate explicitly the reflections. Psi. It can be calculated explicitly. So this will be identity. So let's write the operator in this subspace, okay? Because I don't want to introduce in the rest of the complement of the subspace, it is identity, okay? But inside the subspace, we can decompose the identity operator into the using the basis, right? So -2, 0, 0, right? So this turns into 1, 1 minus, okay, that's fine. 1 minus 0, 0, that's correct. Which is, let's call it, because it is Pauli operator, the Z operator, right? The diagonal one, right? Which is fun. And the other guy, you can do the similar algebra here, but there is way more terms. Trigonometric identities has to be used, but in the end, believe me or not, if not, you can check it for yourself. But you can make it into cosine of twice the angle sigma x. No, sigma z. Sorry. Sigma z minus or plus, I wrote it plus, that's maybe correct, sigma x, okay? With sigma x defined in the standard way, so sigma x would be 0, 1 plus 1, 0, right? Sigma y similarly.
So basically it seems that they just say you had this r psi and r phi, now you just wrote smartly in the sigma x, sigma y, so now you can use the usual e to the power whatever. I think the algebra and the proof becomes easier.
Yeah, exactly. This is the whole trick. You reduce everything to two-dimensional space where you have your Pauli matrices. Everything is easy, rotations, everything is nice and easy to parse. And this formula. So if you remember an assignment from first lecture probably, or maybe second lecture, or whatever, you might recognize here that this guy here is they want to invoke it right now. No, not yet. It's almost. This is the formula. And now looking at this, now if you imagine that we take a product of those two reflections, phi, okay. We are constructing here, so this will be sigma z acting on cosine twice sigma z plus sine sigma x. Okay, so we are like Pauli matrices are very nice because this all will reduce into cosine of identity minus probably plus. I wrote plus. That's maybe true.
Yeah, because it's cyclic.
I sine twice sigma y. Okay, and now we recall the
And t to the power I theta.
yeah. Now we recall the assignment from lecture 1 or whatever, and we see, oh, well, this guy is actually e to I theta sigma y. Okay, which is very, very cool. And now, so this is almost good because you might recognize that this is like, oh, this is like a rotation
in the subspace.
In the subspace, but the angle is a little bit too big. It's like angle is 2 theta instead of, so if we take this guy and apply it to psi, it wouldn't lead us to phi, but too far.
Mm-hmm.
The angle would be too big, right?
Mm-hmm.
So we have to half it. We need 1/2 of theta. So how can you halve the angle? Well, let's take a square root of this operator, which is scary because you have, this is like a complex phases here, and there is some scary stuff because with complex numbers you can there is ambiguity how many times you revolved, and square root is an inverse function, so it's if there is ambiguity, then it's not well defined. So have branch cuts and stuff like that. However, since theta is smaller than pi over 2, there is no problem. Its square root is well defined, and it's in this case it's unambiguous.
So the theta, what's the lowest value? Because when you say pi less
Okay,
than
between 0 and
yeah,
2.
so 0 inclusive, right? Yeah.
Well, probably because there is nothing to talk about if theta is 0.
No, if theta is 0, then you will end up with psi. So you should exclude theta, right? Because they should be always orthogonal.
Theta less than 2 pi is fine.
No, whether to include 0 or not.
No, bigger than 0,
Yeah.
because if it's 0, there's nothing to do. It's identity.
No, it's not identity. You'll end up with. I was thinking about phi, because then phi will become psi, but then you will break the orthogonality requirement.
Yeah, it's just one dimension.
Okay.
I mean, you don't break, but it's just the same vector, right? So it's nothing to do.
True.
Nothing to do, right? So in other words, if I take this 1 minus 2 psi, the reflection composed with the other reflection, you might be wondering why the hell are we doing those reflections? There is a reason. And we take square root of this guy, which, because theta is smaller than 2 pi, this is well-defined operation. This will be equal to I 1/2 theta sigma y, which is a spin operator actually, a y component of spin operator. This is a proper rotation. And now I take this guy, let's call it u from psi to phi, probably. I wrote it from psi to phi, and yeah, it's correct. And now if I act with psi to phi on psi, actually, we will get phi, which you can see. I mean, you want me to do the algebra? where is it? 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 Here it is, right? If you break this down, I mean the down. Okay. You know, let me write it because you probably don't believe me because I am a liar. Minus 1 over 2 theta, right? On psi, which is 0 vector or 0 basis vector. So this is cosine theta 1 plus I sine theta sigma y acting on 0. So this is cosine theta 0 plus sine theta 1, because the imaginary unit will be eaten and the sign will remain. We have a flip, and this is phi. This is phi. This is phi. Which is so we executed a rotation, and it's also the direct rotation. This is actually the most efficient. To actually show that this is the most efficient, you would have to like prove it. I won't go into that. I mean, I don't think even the guys here, they just comment on it and give a reference that this is the shortest possible transformation that does it all. You can actually also figure out that those reflections lead you to all those rotations with doing sketching, geometry with geometric arguments. I actually went and did it, on the blackboard. I was like drawing the lines, was confused. But if you actually go through it, you can actually see that the angle will be twice as big, but everything will like reflect on reflection, on reflection, on reflection. It's a nightmare. But you can actually see it geometrically. But algebraic calculation is way more transparent, I think. So there are a couple of things about this guy that we can immediately notice. So if we take the generator of this transformation, so S from psi to phi, which formally is a logarithm of this u psi phi, right? And it is actually for us equal to I over 2 theta sigma y. Okay, it's an anti-Hermitian operator, as it should be, as a generator of unitary transformation should be. It is a block of diagonal in a sense that if I want to do the projection onto phi, on the psi subspace, one-dimensional subspace of this S phi to phi, or I will try to do the projection onto complementary subspace. Of this S phi. Okay, this will be 0, which you can like check it out. With psi, this is easy because psi is one of psi. I lost my cursor. Right, this is equal to 0, right? And sigma y is an off-diagonal matrix. So you can easily imagine that this is the case. This is true, but it also turns out that the other way around also works. This equals the complementary psi phi it's also 0.
So basically, S will never take the state to itself.
Yeah, it's a block of diagonal.
Yeah, okay.
This case, blocks are one-dimensional, so it's like purely of diagonal. But in this span of, I mean, this is what it means. Here it may be like awkwardly written, but we will generalize it in a second to higher dimensions, where it will be
But,
clear.
yeah, I mean, you just wrote it, but it's kind of clear from that sigma y structure. If you look at, so basically, you're writing down the matrix elements for that sigma y in the psi phi basis. Okay.
Yeah. And the other thing is that the norm of the generator, it's also like small. I mean, it's bounded. It's bounded, right? Actually, we can calculate this guy easily. And the length of sigma y is 1 because its eigenvalues are 1 and minus.
Maximum eigenvalue, right?
Yes, but it's a 1 and minus 1,
so
and the absolute value of the eigenvalues is 1, so this is 1. So it's actually theta over 2. But what is important about it that it is less than pi over 4. It's less than pi over. This is what we will ultimately need.
Okay.
For the square root to work, basically, and some other stuff, when we generalize it. But this is actually smaller, it's pi over 4, which is smaller than pi over 2.
Yeah, but the pi over 4 is stronger condition, right? Now if you are somewhere between pi over 4 and pi over 2, you'll run into trouble because you will be violating this, right? Can it stay consistent?
Pi over 2 will be and is required to the square root to work. To be that's all we need, and some other stuff. In this case, this one-dimensional case, it's actually the norm is actually smaller than that, even than that. So we are safer. We are even better in a better position. And this is, I mean. Okay, well,
okay, so the logic is norms S is actually less than pi over 4, but we actually only need less than pi over 2. Is that
we will be need,
okay, then now the logic is clear, okay.
Yeah. This is like because this will be.
We only need a looser condition, That's why it's,
Because we now go to, so this was for two vectors, direct rotation between two vectors, so single dimensional subspaces. But what we really need is a generalization for direct rotation between multi-dimensional subspaces. Actually, what will we want to execute, because maybe you are trying to see where we're going with this, we'll try to construct, I mean, the Schrieffer-Wolff transformation will be basically direct rotation between the low energy subspace of unperturbed Hamiltonian to low energy subspace of perturbed Hamiltonian. So it's so we need direct rotation between multi-dimensional subspaces. Okay. And this generalization, so generalization of direct rotation, direct rot to multi-dimensional subspaces. So imagine we are emailed two projection operators, P alpha and P beta, okay? Two projection operators. So they are projection operators, so they satisfy, if you square them, you just get them back, right? That's what they are. So all those projection operators, you can use them to carve out a subspace in your Hilbert space. So let's call those subspaces like P alpha H, okay, and P beta H. This kind of notation, it insinuates that you take vectors and you apply your projection operators to cut out only stuff in the subspace it projects on top, right? The rest goes to 0. So this is like a shorthand notation for that. And now the direct rotation can be constructed under some conditions. We'll get to conditions in a second. The direct rotation between this subspace, alpha subspace and beta subspace, is given by, so u alpha to beta or beta to alpha. I wrote it alpha to beta, which is maybe true. Would be a reflection operator twice p beta 1 minus twice p alpha. You see the parallels here. This is also this. So this reflection operator, what do they reflect? They reflect the subspace, alpha subspace, beta subspace, right? And leave everything else. This is like a direct generalization of the reflections we looked at previously, and the square root. So we have to explain ourselves. There will be some conditions so that this makes sense, the square root makes sense. So let me introduce a special kind of notation, because this I can break it down into 1 minus p beta minus p beta, right? And this operator here is also projection operator, but on the complementary subspace, right? So let's call these guys q beta, okay? Because we will be using them a lot, so it's good to have a letter for them. So we can write it as q beta minus p beta times q alpha minus p alpha and square root. And this guy will have a generator, so let's call it S alpha to beta, okay? So I'm claiming, without explaining myself yet, because there will be some restrictions, that this guy will execute direct rotation between those two subspaces, that this will make sense, and it has generator, and this generation, if this all makes sense, then the generator will have similar analogous properties to what we just wrote down previously for one-dimensional stuff. So we'll have a well, 1 for 1, u alpha to beta acting on p beta, sandwiched between u and u dagger. This rotates us to p alpha, okay? And the same is true for the complement, q beta, alpha beta dagger also rotates us to the complement of alpha, okay? This is direct generalization of what we had before. And the generator will satisfy two things. For one, p alpha slash beta s alpha to beta. So we'll have block diagonalness, if this is a word even, probably not. Alpha beta s alpha to beta q alpha slash beta 0. Okay, so it's only block of diagonal elements are non-zero. And two, the norm of this guy is no greater than pi over 2. Okay, this of course would have to be proven, right? The proof goes more or less like, okay, you have those subspaces, but you have projection operators, but you can like cut it into at most two-dimensional like subspaces, and for those the previous arguments basically work, and it's like you construct it downwards like this. Details are again here if you want, and many more many more like proofs of the uniqueness and stuff like that, which I don't think we need to go into. So all this will work under the condition that those alpha and beta subspaces are not orthogonal to each other, right? And how do you non-orthogonalness of subspaces? How do you even quantify it? How do you measure it? Well, there is a very interesting condition. Direct existence condition, and it actually goes that 1 is greater than the norm of p alpha minus p beta. So the norm of the difference between projectors must be smaller than 1. Okay, which also in this case is also the same as saying that the norm of q alpha p beta should be also the same as the norm of p alpha q beta. Okay, so you have those three operators will have the same norm, and it must be smaller than 1. So as it turns out, what this means, this condition means that no vector in the beta subspace is orthogonal to any vector in alpha subspace. Okay, so all vectors in subspace alpha are non-orthogonal to vectors in subspace beta.
Basically, everything overlaps.
Yeah, kind of. I don't know how to imagine it even. It's kind of sounds wacky, but this is what it means. If there was at least, there was even one pair of vectors that are orthogonal to each other, it turns out that this norm would immediately snap to 1. So you can see the detailed considerations in the paper if you want to learn more about this. But this is kind of weird. I cannot imagine it. It's because it's multi-dimensional. All the vectors are not orthogonal. I guess so.
For me, I just think, okay, orthogonal 0 means they don't overlap. I just use that terminology. I don't try to visualize it, but
the second thing is automatically also mean that the dimension of alpha and beta are the same. Otherwise, it also will be this norm would also automatically snap to 1 if the dimensions were mismatched. So this is actually this one guy contains all of this. Right? It contains that they are no vector is orthogonal to vectors here. It's never possible, and the dimensions are the same. So it's actually like you taking the one subspace and rotate it a little bit with respect to the other, but not too much, so that nothing gets orthogonal. I don't know how to imagine it in your picture. I don't know. It's something. But this is what they tell me.
So it's just like the special case, right? There also you are rotating in the small arc.
Yeah.
So
This is exactly.
it's the same structure.
And when this is satisfied, you can then show that this is well defined, that this square root exists, and this S is unique. This generator is uniquely determined and has all those properties. It's all tied to this condition, which is a multi-dimensional generalization of non-orthogonality between things we want to rotate one into another. So this is a geometric thing maybe it's good to know, to have it back. Maybe it come up someday. But for us, it's the best thing about it is that because ultimately what we want to do they have some nice ways to put it. Yeah, because what we want to do, we want to our Schrieffer-Wolff transformation would be, okay, so with this knowledge about direct rotations and subspaces, so we will have what we are trying to achieve is like we have a projection operator, let's call it P0, which would be a projection onto below, onto B. So eigenstates of the unperturbed Hamiltonian, right, if you remember. And we will have a projection, let's call it P lambda, which will be a projection onto low energy subspace of the perturbed Hamiltonian. Okay, if you recall how we denoted the eigenstates. So those G. Something is missing here. So those are two projection operators. If the strength of the perturbation is smaller than the gap, we already talked about this, that it will preserve then the gap for the perturbed Hamiltonian as well, which automatically also means that the dimension of this subspace will be the same as the dimension of this subspace. So we are getting closer to this. So maybe we are closer to fulfilling the condition for the direct rotation to exist. So we will have to check that actually the norm, the difference, is less than 1 to actually know that direct rotation is possible to exist. And once we check that, we can take our Schrieffer-Wolff transformation as this direct rotation, okay? With this generator, and the procedure will be to evaluate this generator in the perturbative manner, okay? And because this is a direct rotation, so this is the most efficient way to do this transformation. So it's this S, this generator will be the smallest possible. So perturbation, doing perturbation theory on it makes sense, right? Because maybe cutting off on the low order will be a good approximation of actually what's going on. So this is like the kind of logic. So we would have to demonstrate that. So to make sure that direct rot between P0 and P alpha exists, we have to demonstrate that P0 minus P lambda is less than 1, okay? And so let's do it. So let's try to do it. And here I have a kind of bad news, because I was trying to figure out. I had this dream. In the paper, okay, they give a proof, which is very nice. It works, in the sense it works. However, it's kind of tricky. It's like using some kind of a trick that I don't feel it. It's not very intuitive. However, I tried to do it other way around, using some other methods that I know will come back in second semester. So I was like, oh yeah, now we can tie everything together, use the same resolvent method to show it. However, the cool method that using resolvency like that and so on, which we would be utilizing next semester anyway, unfortunately it overestimates this difference here. And it overestimates it to the point of uselessness. That you get something that you cannot be sure that it's less than 1. And it's like, God damn it. So we have to use the tricks. And the tricks gives you very nice estimation, very tight estimation. Actually, the method they are showing, which maybe I will comment on in a second, gives you that the difference between P and P alpha lambda, which is actually the same as taking the norm of what kind of zeroed alpha, which is first? P0 Q alpha. I want to be consistent with my notes. P0 Q lambda, okay. They show that this is less or equal to actually twice norm of the perturbation divided by the gap, which is a very nice estimation. So so in order to fulfill our condition, this must be smaller than 1. So this is a constraint on how strong the perturbation can be with respect to gap. So if this was to be smaller than 1, then this means that the lambda v must be smaller than half of the gap, which is something we already talked about. So the perturbation, it is enough if perturbation is too weak to close the gap. Then, as it turns out, those low energy subspaces will have the same dimension and they will be non-orthogonal. It's like, okay, I guess. But for us, it means that we also can execute direct rotation between them. So so it's like, it's perfect, right? It's like no extra things. We are not required to do any extra thing to actually have a direct rotation. So it's like perfect solution for our purpose, for finding our Schrieffer-Wolff rotation. Okay, we good? And so we already know that this generator of our, which we will try to find perturbatively in a second, it's a block of diagonal, and its norm is bounded by pi over 2. And the particular block of diagonalness, I want to focus on it for a bit, because this is something we like when we are doing our gorilla, going straight forward without thinking, doing the solution last lecture. We're like, oh, this equation seems like suggests to us that maybe we can set it to be purely off diagonalness. Let's just assume that it is. If it's not, then we will be in trouble. But if we are right, we will be cool. But here we have from construction, we know immediately that it's actually a block of diagonal. So instead of guesswork and worrying that maybe you are guessing wrong, there is no guesswork. It's just truth by construction. So very nice, I guess. And probably time for break. Sure is. Sure is. As usual, I'm taking so much time with this. But this was the most important construction, I think. Yes, so let's take a couple minutes break. And then we get back to it.
So, yeah.
All right, so we're back. So we talked about, right. So Schrieffer-Wolff transformation, it's like on the geometric level, it's a direct rotation, which we just checked that if perturbation is too weak to close the gap, it exists, it's well defined, it has a block of diagonal generators, so it's like, this is the basis of what we are doing. So now that the plan I wanted to implement was the following. Yeah, okay. So the plan. The plan. We know the direct rotation exists. So the plan was like, first step would be to define. Maybe I would just say it more. So plan would be define a procedure. Procedure for generating perturbation series terms, right? Because it's like, if you want to do a perturbation theory, you have to, first you have to like have terms of your perturbation series from some place. There is some procedure for doing that. On previous lecture, again, we didn't have like any framework for that, so we just like, what if we substituted generator as a series, put it into the formula for diagonalization, just expand everything into power series and compare terms. That was our procedure back then, without much forethought. It's a good first guess. So here we can like do maybe a little better about that, and try to find a maybe more well-defined procedure for generating those terms. So once we have the terms, we have this generator. The second thing would be to diagrams. Because any good perturbation theory, once you have your formulas for terms of your perturbation series, there are probably some complicated mathematics behind it, so you want to have a graphic representation so that humans can parse it. So we would, okay, what are the diagrammatology for Schrieffer-Wolff transformation? So that would be step number two. Now step number 3, once we have that, we have structure of our perturbation series locked down. We can calculate this stuff, so the last step would be to, okay, but does it converge? So radius of convergence. Estimate the radius of convergence. And the plan, I had this ambitious plan. I will see how, I don't want to go over time too much because I'm tired and old and sleepy. But there are a lot of details associated with this. The radius of convergence we can actually estimate. There is a way, although maybe I can if I may, if I'm allowed to say this, like I said, everything is based on this paper. However, the estimation of radius of convergence, I realized that they kind of underestimated it a bit. They didn't notice that they could like reuse some tricks they used previously. So the radius of convergence they obtain in this paper is like at least factor of 2 smaller than it actually can be. So we can make it even better. So it's a very good paper, everything is very nice, but the one thing slipped there, they didn't notice something that they could improve their results. So if we get to radius of convergence, we can see the improvement on, yeah.
So we have 3 things. So just a question about where we are going. So these diagrams, is it like similar? Will it help to understand the other structural diagrams that we draw in field theory and so on?
Not really.
I don't mean exactly, but will it help to understand the logic or some sort of structure or something?
It will turn out that Schrieffer-Wolff, this series, its diagrams have a topology of trees.
Mm-hmm.
There are 3 diagrams.
Mm-hmm.
It's actually not that uncommon. I believe Magnus expansion, which we'll talk next semester, it also tree-like diagrams. But if you think about field theoretical Feynman diagrams, they are not trees at all. They are more like there are loops there, but it's like the connections. There are like multi-connected networks. I don't know what the word for that is, but it's not like, you know, splitting branches with leaves at the end. So it's like topologically completely different, which means something, I guess. So understanding Schrieffer-Wolff diagrams don't help you with Feynman diagrams, because topology is completely different. So this is basically our first diagrams that not real perturbation theory, but the diagrams we wrote were like the simplest linear topology, nothing there. So this is like next step of evolution is from linear to trees. And maybe is it next step to go to Feynman diagrams to have networks from trees? Maybe not. Maybe it's a side branch of evolution. I don't know. But yeah, that's what will turn out. So let's try to follow this plan then, and do some weird tricks to actually get the procedure in works. Oh yeah, so I won't comment on the way actually you get this estimation. It's kind of weird. It's like uses something called Sylvester equation, which is, they say it's known from control theory and metrology. I asked my friend who's doing like metrology, and he, oh yeah, I know something about Sylvester equation, but how you make a connection to arrive at this, I have no idea how they did it. But maybe if you have a lot of experience, you can like see it somehow. It's like super tricky, and well, you can check it out in the notes or in the paper itself if you are curious, or we can talk about it later. So we will skip that then. So the procedure for generating the thing. So the step one here. And this is unfortunately also kind of like tricky, but the tricks we will be using here are not completely without precedent. This is well-established trickery that dates back to Lie algebras. It's like you have a lot of, you have some matrix problems to solve, and you have some generators. So you have an exponent of some matrix, and the arguments of sort that let's assume that the generator is infinitesimal, because if it works for infinitesimal, it will work. You know, it's like Lie algebra, Lie group stuff kind of arguments, and we'll do something like that here as well. Okay, at least we will try to. So this step one. So we start by writing down the action of our direct rotation. I don't remember where the minus should be. It's here or here, whatever. Up to minus, it will be fine. And first, so it will be convenient to actually rewrite it as an x of a super operator. So let me write it as a e as, I always mess this up, ad of s acting on h plus lambda v, where ad is from Lie algebras, it's an adjoint associated with s. So what it means is you are taking a super operator that is a commutator with s, the stuff in here. So A bullet is like a placeholder. So you imagine adjoint. For some reason I always write D first instead of AD. There's some reflex here. So if you act, because this is a super operator, this is a linear operator acting on operators. So we are like, advancing on the ladder of abstraction. So this would give you S with X commutator, right? This is how you parse it, adjoint. And Y sandwiching with S and with a unitary and the unitary daggered. Y it boils down to this kind of formula. Exactly. You can. This is like a thing that pops up all the time, right? Actually, there was some assignment a couple of lectures ago to actually see this happening, because we already saw like nested commutators. Because if you take a power of adjoint S, adjoint S on X, what will you get? You will get S on X, a nested commutator. I think this is like a Lie algebra stuff. It happens all the time. Here it happens all the time. And also, like, when we get to Magnus expansion, it will happen all the time. So get used to it. Open systems, quantum open systems, if you do some more advanced work at it, happens all the time. It's like adjoint is your friend. Although which notation to use, this is kind of wonky, but it's also kind of standard. So we will use this silly ADS. So we rewrite it in this way. This adjoint then would be a generator, which will, from time to time, we will bring up the argument in the form. Let's assume that it is a infinitesimal generator to do some Lie algebra kind of tricks. And these kind of arguments will work because what we are trying to achieve here, we want to find S that is an analytical function of the perturbation strength of lambda, right? So it makes sense to, if you look at like that, it makes sense to like manipulate the magnitude of lambda. So you can take it very, very small, that would give you a infinitesimal value. This kind of manipulation, they basically come from this, because ultimately you are trying to find S in an analytical form. And as a reminder, analytical function means that it is a function that can be represented as a Taylor series, power series, basically.
What is the Lie algebra underlying this?
Sorry?
What is the underlying Lie algebra?
It's just methods of Lie algebras, in the sense that you have an exponent of adjoint. Okay. There is Lie algebra here because we are doing unitary transformations. Unitary transformations form a SUD group. There is algebra on top of that. The picture we draw here. This stuff, it's like, it's almost a manifold of. This is.
Yeah, because here
unitaries are the
because I
groups.
think the logic there is it's similar to what they do in GR. Like you have this Hilbert space, and then you map this Hilbert space onto a block sphere or sphere. But now the problem is you cannot use the usual metric on the sphere, which is like the you need to take information from your Hilbert space and construct distance motion here.
I want to talk more about this group stuff when we get to in next semester, because we will be talking about time-dependent Hamiltonians, so there will be room for that. But there is actually Lie algebra. We are dealing with Lie algebras here, but we don't have to know about it. We just have to know about tricks, adjoint basically. So this is one comment. And now the shenanigans begin. So I'm basically following what the guys in the paper are doing. I'm not sure how one arrives at this kind of things, but I guess they did. They have some experience with stuff, but it's really crazy if you look at it. So what they are doing, the first thing they are doing is like, okay, so we can like do some add and subtract some stuff. And they say, let us add here EADS plus EADS and 1/2 acting on H plus lambda V. And let's subtract, oh sorry, minus here. EADS minus E minus ADS acting on H plus lambda V. So you see what we did here? We took this guy, split it in half. So that's 1/2 here, 1/2 here. And we added E2 minus this adjoint and subtracted E2 minus adjoint. So the net, nothing changed, right? However, if you recall your trigonometry, what we did here, we have here a hyperbolic cosine of ADS acting of H plus lambda V plus hyperbolic sine. Okay, in the sense that when you write down the power series decomposition, you get a series corresponding to cosine, hyperbolic sine, which maybe let me write it down because it's actually relevant for the argumentation. So hyperbolic cosine involves even powers, right? It's like x, but even powers. Okay, factorial, which also means at the same time, because it's basically x. When x is a blessed function, right, and so on and so forth, everything converges, everything is nice, everything is good, to power 2k, right? And this whole beast, this whole series acts on H plus lambda V. And the sine is odd powers. Should I have some? No, minus is unnecessary. Plus 1 factorial ADS 2k plus 1. Acting on the thing. So this is a trickery we are doing. And now the arguments come in. So, one, after what we expect, what Schrieffer-Wolff transformation is supposed to do, or this direct rotation is supposed to do. So it takes a block diagonal operator, block diagonal low dimension subspace, high dimension subspace, and it transforms it into a, again, block diagonal operator, but in a, well, this is a block diagonal in the low energy subspace of a perturbed Hamiltonian and the higher energy of perturbed Hamiltonian, transform it into block diagonal in unperturbed Hamiltonian subspaces, right? But the point is that when this whole thing, when it finishes its job, you must have block diagonal operator on the right hand side. Okay. Now, S, the generator, is block of diagonal. Okay. So action of adjoint, it basically multiplies operator with S, right? So it's like if you are acting adjoint on a block diagonal operator, you will get block of diagonal operator, right? If you act on it with S again, or adjoint of S again, you go back to block diagonal. So essentially, even powers of this adjoint of S keeps you in a block diagonal space, let's call it. Odd powers kicks you out, right? So, having said that, we can figure out that the cosine, hyperbolic cosine, acting on, let me write it. So cosine, hyperbolic cosine, so odd, even powers of adjoint, acting on lambda v, which is lambda v itself is a block of diagonal in the space of unperturbed Hamiltonian. Okay. Cos is even powers of S, so it will keep this operator in block of diagonal space. Okay. And the other term, sinus, hyperbolic sinus, at S, acting on H. This will do, it takes H is block diagonal, even powers of adjoint S will kick it to block of diagonal also. So these two guys are block of diagonal. And they are on the right-hand side of this equation. But we cannot have that. It must be, everything has to be block diagonal on the right-hand side. So we have our equation that this has to be 0. Okay? Otherwise, we would get something that's not purely block diagonal on the right-hand side, which is cannot be.
That's not our aim. That's the logic, right?
Yeah, I mean, this is not what S does.
Yeah.
This is not what this transformation does. So S must be such that it zeroes this equation. I mean, satisfy this equation. So I told you there will be a lot of trickery. It's really like a thing. But this is just the beginning of trickery. Now the thing comes in. This is the thing that I have no idea how they come up with this shit, man. It's like goddamn, man. So they are saying, since we are looking for S that's analytical, so we can like do this equation has to be satisfied by S, but also infinitesimally small s has to satisfy it. This is what they say. If we assume that S is infinitesimally small, or the adjoint of S is infinitesimally small, then sinus can be inverted. So let's take invert S, this superoperator, invert superoperator of sinus, hyperbolic sinus of adjoint S, and let's act with it on the both sides of this equation.
What's the logic here? I didn't understand.
It basically means that look, if you are doing if the argument of the hyperbolic sine or any trigonometric function is small enough, there is no problem of being like having like a how do you say it, ambiguity.
It's bijective in there.
Yeah. You're keeping it biject. So inverse function exists in the sense that there is no problem of convergence of the series that defines arcus hyperbolic sine and stuff like that. So this is a trickery which you take directly from Lie algebra. This is the algebra tricks. This is what Lie was like doing left and right. So we are just they somehow knew that this will work. I mean, okay, I guess. So they're saying let's act with arcus hyperbolic. Well, not really arcus. It's this superoperator, the inverse of this superoperator. Okay, but that's not all. They say let's also smash just adjoint of S on top of that. So act with this first, and then act with ADS. Okay, I guess. So the right-hand side is easy because it's 0. That's fine. Okay, 0. Here you will get so inversion. So this hyperbolic sign will just cancel. So you will get ADS on H. Okay, that's fine. I guess it's fine. And here you will get hyperbolic sine adjoint S to -1 acting on cosine adjoint S lambda V and adjoint S. God damn it. There is something wrong with my brain. I cannot write it ADA is what I want to write. There is something wrong with my brain here. And actually, when you look at the series expansion of this beast, you know, thinking that ADS is actually infinitesimally small, this is actually the same series expansion as hyperbolic cotangent of ADS, because it's like cosine over sine. It's the same series actually, which is like okay, I guess if this is what we're trying to do. And they actually say, let us deploy this series expansion of this guy. So basically, they say this function, because there's S adjoint S here, cotangent here, right? This guy, its series expansion is given by from 0, I think from 0, yeah. 2 to power 2k divided by 2k factorial times Bernoulli number 2k, which is, get used to Bernoulli numbers. For some reason, they are all over the place. There are Bernoulli numbers, so special tabularized numbers that in ancient times Bernoulli came up with, and they are everywhere for some reason.
The solution of the Bernoulli's equation,
There are like billion, connections.
Function, right?
Look, this is old school stuff.
I don't know if they're the same. It's the same guy. Yeah.
This is an old school stuff. So it's like you have whole books and tables of various identities, relations, generalizations, and you can find billion stories about Bernoulli numbers, but they are all over the place.
This is the same name as Bernoulli zone, right?
no.
Is it?
Briolen and Bernoulli. You think about Briolen.
Yeah.
That's different.
Yeah.
Bernoulli is like real old schools, like 18th century, maybe earlier. Who knows? So it's really like super old school stuff, right? Okay, so we are then. So where we at? We are at minus. Let's move this adjoint SH on the one hand side, and let's leave this guy here, which is in the form of this series, which I just wrote above. 2k, Bernoulli number, factorial, and adjoint S to power 2k, acting on lambda V. Okay? Whew. One more thing to note here. One thing to note here. Look, what is this? So this is minus S commutator with H. Okay? But this is just one minus away from S commutator with H, aka adjoint H on S. This is a thing to note. Okay, so we can We can rewrite it even more. Adjoint H on S, and this whole series here, which I don't want to write down, but I'm already started, so I cannot stop now. ADS to power 2k lambda v. And now another trick, which is also this I kinda can trace origins of, because there is a so if we could just like invert this adjoint of H here, right? Then we will have S on the left hand side, right, and some stuff on the right hand side, right? That would be cool. That would be formula for S, essentially, right? Is it now? Yes, it is now. So how do you invert adjoint of Hamiltonian? Well, there is a certain standard form that actually does that, and we've already seen this guy, but not in the form of superoperator. So let me introduce a kind of inverse of adjoint of H, which I will call L. It's a calligraphic font because it's superoperator. So if this superoperator acts on L, on some operator X, this is how it does it. So you take a sum over energy levels of Hamiltonian. You take a matrix element between A and B, okay? Matrix element of what, you ask, naively? Well, of a beast that take a kind of projection of operator X onto off-diagonal block of diagonal space. So you take X and sandwich it between P0 and Q0. So you take cuts, leaves only stuff that's on of diagonals, okay? But you want to be, it has to be symmetric, so it also does something like this, okay? All right, all right, all right, all right, all right. Then you have a divided by the omega IB. See why it's not, we already seen this kind of thing. A matrix element divided by the energy difference, and the superoperator has to bring us back to the operators. So BA or AB? I wrote it like that. Okay? Yeah?
Quick question. So what is our aim? Overall aim?
We are trying to do some shenanigans to generate the procedure for creating terms of series.
So series means like
For
S.
series of S, yeah.
Okay, yeah, no, okay.
So it's like the aim, you will know the aim when you get to the end. I just, look, it can look like this, but there are lessons to be learned here. One, we became acquainted with adjoint. That's cool.
Like that superoperator, I think probably the structure might be the same, but it's like I'm not used to seeing.
Yeah, it is kind of. I mean, I wanted to see how crazy this goes, but this kind of like inverse operator, because they use argument. This I feel this is kind of good. This is kind of good shit. Okay, this is probably will come handy, and I'm almost sure it will come handy when we'll be talking about Magnus expansion anyway. So this is like what's going on? Where there is something to steal from this. Okay, there's probably we can do some stuff with that in the future probably. And Bernoulli numbers came up. They always came up, and I don't know why. And now maybe I will know. Okay. And this guy also it's everywhere. This divided by the energy difference, and this is how to learn that it's kind of inverse of adjoint of H is kind of useful, because it actually is. And I don't want to do calculations in front of you, but if you actually now take this L and you apply it here on both sides of L, you will actually get S. It inverts because S is already block of diagonal, it actually reproduces S automatically. And you will get this series here, which we are almost here. Because there is you might see, oh, this is a formula for S. I mean, why? We don't need any series. We're done. We have a formula for S. What more we need? However, you see, S is here, but S is also here. You have a nested commutators with S. So it's not that simple. It's a whole thing. So so we cannot avoid going through the motions of perturbation theory here. Okay, this is we cannot. It's not the solution of this equation yet. However, so now we come to the thing where we say, okay, so now we are looking for analytical S in an analytical form. So S must, let's assume that S is has an expansion, power series expansion. Okay? We can treat it formally as a function of lambda. Why not? So now we take this, we cram it in here and here, and we compare terms of the same order in lambda, like we did before. And when we do that, we get our iterative solution, basically. We get our procedure. Because once you do all this bullshit here, you get that, for one, S1 will actually be equal to this L acting on lambda V. Okay?
How can you still have lambda? I thought you're looking at the order, right? So lambda should drop off, right?
V has its own lambda, so it adds.
But
Yeah. This lambda. Okay. Sorry. I know what you mean. Yeah. On V.
Okay.
Yeah. L on V. Yeah. Okay, so that's the first order. We need first order because this is inductive formula, I guess. Because for k plus 1 equals, and now there is a sum here. So the sum comes because we are collecting powers of lambda, and they will imagine. So we have nested commutator. So to power 2k, each instance of this adjoint brings its own series expansion of S. So imagine that it starts to proliferate. The lambdas start to mix. You can mix and match them.
So you are assuming that you can. You are assuming. Do you need to assume uniform convergence, because I guess you are, or absolute convergence, because you're moving around.
Yes. This doesn't work. It doesn't work if we are operating outside the radius of convergence. But for now we
doing it. Okay.
Let's procedure is under assumption that it works. Then we will have to check what are the limits, what is the maximal value of lambda that allows us to do this. So we have sum over n, we have Bernoulli, the coefficient here, Bernoulli number, and all this stuff. Once we collect everything, and here will be a very weird sum, which I will write it like this: L A D S K N A D S K1. Okay, so we will have n indices, K1 to Kn, acting on V. Okay. What about those indices? So if I believe I introduced the notation for tuples at some point. So tuple Kn minus 1, K1. Okay, it's a ordered sequence of numbers. Okay, a tuple. So we will be summing over these kind of tuples where the values of each this component of a tuple can go between 1 and k, where k is this order right here, maximal order, to the power n. Okay. Under the constraint, I will write as that the norm 1 of this tuple is k. This basically means that when you add all the ki from 1 to n, they add up to k. In other words, here you see those orders of s's comes in, and you collect everything where the total order adds up to k. Okay? There is extra lambda from v. That's why this is a formula for s. So this is a procedure, and this is it is soluble because by construction you can see that sk plus 1 is given by s's of only lower order, right? There is only orders lower than k plus 1, nothing greater than that. So this is fine. This is soluble. You can go iteratively, starting from 1. You can get 2, you can get 3, and so on, and end whenever you wish. It kind of looks extremely annoying to parse it, what's going on. There are some conditions. That's why you need diagrams here. And the diagrammatic representation, as I mentioned previously, let me just finish this the diagrams, because with diagrams there are rules and you have to I just explained in words why they work. There is no other way around it. But I said that diagrams have a form of a tree, which actually kind of makes sense because when you start here, we are here, right? You put here S in the form of a series, right? It will like spawn into like branches, right? You will have a lambda to the first power piece, second power, fourth power, and so on. So you can see that at each order you will get you get branches essentially, like in tree. Okay, so you see this because you take powers of series, they will have they have tendency to proliferate into multiple branches. If it makes sense, right? You see it, kinda. The tree structure, where it comes from. It's like a Pascal tree, right? The same kind of thing here. You can envision it somehow. Kinda, okay. Well, the diagrams, the rules for diagrams. Oh my God. Okay, I have to go over it.
Maybe you can show the notes and just walk through. Might be faster than writing it.
Yes. So
you don't stop abruptly. And do
yeah, because my
faster.
brain is getting toasted right now. But yeah. So let me draw a diagram and then explain what's going on here. So let's say the actually second order diagram will be 0, as it turns out. Actually, S2 is 0, which you can work it out if you write it down, right? You can check it out. Only odd powers are actually non-zero. So the third order diagrams that will come in, because the third order is as usual with diagrammatology, the order is given by a sum of diagrams with weights. This is how it typically works out, okay? So the procedure is that you you have those rules for constructing diagrams so that you can draw them. You draw them. You appropriate weights, you multiply by some number, which is also some rule, how to figure out what number has to be there. And then you sum them up, and then you have rules to translate pictures into formulas if you want to do actual calculation. Sometimes you don't even need that. You just, the graphical representation is sufficient.
So something like Feynman diagrams?
Feynman diagrams work this way as well. All diagrams work this way. Okay, the order k is given by sum of some pictures, which when you translate it back into formula, there are some weights to each picture. According to some rule, you figure them out. And the picture can be converted into some formula, which then when you add up everything, it gives you actually a mathematical beast like this. Okay. So third order term, third order diagrams, possible diagrams will be, that will be 1, and the other will be 1. Well, sorry. How does it go? Is it all? Wait, is it all? Because this can be 1. Oh shit, wait. Oh my god, my brain fried. Wait, it's odd. Yeah, it has to be odd, but the number of leaves has to be, holy damn. U has even number of children.
Maybe you can show the notes on the screen. So maybe like when you review it, you can.
Oh my god, I am just too tired, man. Other case is 0. Even number. I also might have made a mistake here.
Ooh, that's bad.
If U is a leaf, yeah. Then you do it like that. If U has even number of children, then it's like this. Oh, no. Fine. Fine. It is a third order. Oh, guys, I'm sorry. I'm just dumb. I'm just dumb. There's even number of children. Did I fuck it up? Okay, so let me. Let's say this is correct. Let's say this is correct. So maybe let's even add some. You know what? Let's do it like this. Yeah, let's do it like this. So this is an order 5 diagram. Okay. So let's break it down. I think this is more correct. Oh yeah. Okay. Order 5 actually will make sense. So this will be 1. This will be the other. Oh, okay. So order 5. This I'm kind of sure this is correct. So every tree, in tree structure, okay, you have nodes. They represent something here. You have branches, and as you can see, branches. And every node has a parent, so thing on top of it, and it has children, or can have children, so things below it. The node that has no parents is a root of the tree, so this is the root, okay. Nodes that have no children are leaves, like in tree, leaves. These are leaves. These are leaves. This is a leaf. Okay, okay, fine. And now the rule is that every node in this tree diagram has associated operator with it. So if we enumerate nodes will be with u, so we have u belonging to tree T, so this is tree T, okay. So there is some operator O associated with u, okay, and there are certain rules what operator goes to what kind of node. And the rule is that first rule is that when u is a leaf, so guys on the very bottom that have no children, the operator you assign them equals actually S1, which is L on V, okay? 2, when u is not a leaf, but it has even number of children, this is important, even number of children, u has even number of children, NOC, and those children we can denote them as u1 up to some uk, okay, and k is even. The operator u assigned to this so let's say this guy here, okay, is given by L on the end and adjoint AD of OU1. Okay, so commutator with operator you would assign to the child up to ADOUK acting on V. All right? Okay? All other cases are 0. So it means that you have your tree. The tree is constructed in such a way that every node can have only even number of children. Otherwise 0. Yeah?
Yeah, I hope it won't fall wrong. Like, so for the fifth order only 2 diagrams will exist, or because now I can imagine why didn't you put, so in the first diagram you have the last 2 leaves, why didn't you put it like, put it there.
Topologically, rotations and like that is just same diagram. Let's say this kind of topological are covered by the appropriate weight, which there is another rule for calculating the weight.
Yeah, so for the fifth order only 2 of them will be
just topologically
distinct in some sense. Okay.
So these are the rules. So basically the trees and the order of a tree is equal to the number of nodes. Okay, so fifth order trees have to have 5 nodes, but in such a way that every node can have either 0 or even number of non-zero number of children. And topologically, if just some topological transformation, this means that the same diagram, okay? So you don't multiply. So for fifth order, you will have only 2 then. This is all you can write according to these rules. Everything else is 0, all right? And using those rules, actually, you can backtrack and retranslate this guy into the formulas. Because for leaves, okay, so I just use this. The guy here, the root, actually, so root has even number of children, so I would compose it like this, in this way. So I need operators I would assign to the leaves then, but I know what they are, I can calculate them. And this is how you work it back up. So, so L is on this very end applied, but actually at every step there is L somewhere. Okay, so it's like complicated stuff like this. The weights, okay, let's not. You can figure out the weights. I won't bore you with the rule. And yeah, so you sum up those diagrams, multiply them by the by the appropriate weight. Here's here, so t prime, okay, and this gives you S5, I guess, okay. Oh boy. I'm sorry, this is just too much for me right now. If you want more details, the paper actually has a full diagrammatology, not only for S, for the generator, but actually for the Hamiltonian on which you rotate with S, okay? And it also includes explicitly the W perturbation, that is the thing that actually works in blocks, which we didn't talk about. It introduces additional rules for the diagrams. So there are more trees, more funny trees than the branches, the stuff, but it's all trees, okay? And the final thing with radius of convergence of this whole stuff. There is a trick to this. I will just tell you about the trick. Oh my God, I'm so sorry, it's over time, but it's the last thing, last hurrah. So actually, you might think, based on what we said previously about the convergence of series, that okay, so we have our diagrams, so we kind of have a feeling for all the terms in our series expansion. So looking for radius of convergence, we probably just take those terms, maybe make a ratio test or something, you know, find the dominating series, make a ratio test and stuff like that, which is what you might try to do. But actually, here they propose a much trickier, and actually I saw it a couple of times, this kind of trick, that because what we want to ultimately show, of course, that S converges, the series converges and stuff like that. But what we ultimately want to show that it is an analytical function. So whatever means we use, that's fine. We want to find a domain where it is analytical. So one of the realizations you can make then is like, okay, but S ultimately is a logarithm of e to power s, right? E to power s is our direct rotation, right? So this is like square root of q0 minus p0 q lambda minus p lambda. Okay, which is also, you can write it as 1/2 logarithm of q0 minus p0 q lambda minus p lambda. So the argument goes as follows. We want to show that S is, as a function of lambda, is analytical. So it can be analytical when this logarithm exists. So we know what the radius of convergence is for logarithm. It's 1. So from that, we can get a constraint on the stuff that's under the logarithm, okay? And from this, you get your condition. So instead of looking at the terms of the expansion, actually that we just derive with the trickery, you do something. You look for the existence of a logarithm. This is something that it will come back later. And using this, you do some algebra, you rewrite it in a couple of ways, but ultimately you boil it down to actually again looking for the norm of. Okay, if you know this, then you can you get your information about the radius of convergence of this guy. Actually, what you get there is like twice this. It has to be less than 1. This will be the condition for convergence of logarithm. Okay, which then translate, because we already know, estimated this guy, we get that our radius of convergence will be, let me just write it, the gap divided by A times norm of the perturbation V, which means that if you look at the function S as an analytical function of lambda from infinity, so this guy converges absolutely and uniformly for lambda that is smaller than this R, then omega A times V. So this is the estimation how big the perturbation can be before everything breaks down. And this is at least twice as big estimation as they actually have in the paper, because let me then finish on this point. So that's the procedure. If you want to do, if you are ambitious enough to do your own perturbation theory, this is kind of what you might want to strive for. Okay, once you figure out in this YOLO manner that, oh, I have something that kind of works, you might then go back and try to do all those steps, procedure for generating terms in some way so that you can have diagrams for that, and then check for convergence by some means. Maybe you can use a trick like this. So looking for analyticity of something, maybe some logarithm actually, and then you are like, oh, this is my perturbation theory with all procedures. So yeah, I'm sorry for extending it too much, but this is the point when we can finish for this semester. Any extra questions? No extra questions, thankfully. So let's stop it here. Thank you.